Swayam Prabha. Digital India. Educated India.
Welcome to the DTH course on micromachining. Today I am going to talk about abrasive water jet micromachining, AWJMM. Acknowledgement from where I have taken some part of this particular lecture from the chapter of Dr. D.S. Miller given in Micromachining with Abrasive Water Jets in the book of Introduction to Micromachining. Hashish Mohammed, a modeling study of metal cutting with abrasive water jets, published in Journal of Engineering Materials and Technology. And Ramesh Babu, lecture delivered on abrasive water jet cutting in a short-term course on micromachining organized by IIT Kanpur. Organization of the talk is Abrasive water jet micromachining, introduction, working principle of abrasive water jet micromachining, machine tools and elements of AWJM and AWJMM system, types of catchers, parametric analysis of AWJM and AWJMM, visualization and applications, and finally conclusions. Introduction to AWJM and AWJMM. Evolution of water jet machining and abrasive water jet machining. How to cut coal mines. Long back in Japan, there were the problems of fire taking place in the coal mines. So Japanese started thinking how to safely cut the coal mines without the fear of the fire. How to cut asbestos sheets. It was found in USA, America, that those industries which were cutting asbestos sheets, some of their employees were having cancerous problems. So they started thinking how to cut these asbestos sheets without the fear of cancer. Then how to dismantle nuclear power plants. Whenever nuclear power plants are dismantled, there were many problems while cutting them and separating them out and taking them away. So how to cut the granites. So the solution was found, and as a result of that, water jet machining and abrasive water jet machining processes were evolved. Working principle is very simple as shown over here. You can see this is the high pressure water tube through which the high pressure water jet is coming over here. This is the abrasive port. Through this port, abrasive particles are coming and they are mixing with the abrasive, they are mixing with the water jet, high pressure water jet in this particular tube, and this tube is known as mixing tube, where water jet and abrasive particles are getting mixed up, and you have the abrasive water jet over here, and here is the workpiece surface. So you can see all these, and this is the orifice. Such type of systems were used to solve these problems of cutting coal mines, asbestos sheets, dismantling nuclear power plants, and so on. Applications of abrasives in micromachining. There are many processes in which these abrasive particles of different sizes and different types are used for machining purposes at macro level, micro level, or even meso level, like grinding, honing, lapping, super finishing. These are known as traditional machining finishing processes. Then there are advanced or non-traditional machining finishing processes like abrasive jet micromachining, where carrier medium is the air and you have the abrasive particles, very fine abrasive particles, and these abrasive particles are driven, air driven. Abrasive jet is there. The problem with abrasive jet micromachining is that it gives low material removal rate. Accuracy is not very high, poor accuracy, and efficiency is also low. However, improvements in jet cutting technology are taking place to improve the accuracy, material removal rate, and efficiency. On the other one, you have ultrasonic micromachining process where carrier medium is liquid. Note it carefully, here carrier medium was air, here carrier medium is liquid slurry. Carrier medium mixed with abrasive particles is known as slurry. Ultrasonic frequency is used for vibrating vibrating the tool, and here you have, as a result of this, again you have the low material removal rate, low efficiency of the process, but these processes have their own applications, and so the improvements are taking place in these processes for improving the material removal rate and efficiency both. Abrasive flow machining is the result of this ultrasonic micromachining, another version of similar kind of the things, where abrasive carrier medium is different than the liquid that you are using in ultrasonic micromachining process. We will discuss it later on. Applications of abrasives in micromachining. Abrasive water jet micromachining. Advantages of this abrasive water jet micromachining is you don't have the dust, no dust, high cutting speed, no thermal stresses, no delaminations, no fire hazards, low level of power requirement compared to other machining or cutting processes, and good, reasonably good edge quality. I don't say very good edge quality, we will see it. And then on the other side, you have viscoelastic material which carry the abrasive particles, and as a result of that you have different processes like abrasive flow finishing process, magnetorheological abrasive flow finishing process, and so on. Now here this viscoelastic material acts as a self-deformable stone. What does it mean? We will discuss while discussing the abrasive flow finishing process. This simply means that the medium itself takes the shape and size of the features on the component which is to be finished. No ultrasonic vibration in this particular case, and use of pneumatic or hydraulic force is there in case of these processes like abrasive flow finishing, magnetorheological finishing, or magnetorheological abrasive flow finishing process. Macro to micro abrasive water jet machining. The extension from macro means greater than or equal to 1 millimeter, to micro less than 1 millimeter machine tools occurred around 90s for laser and wire EDM. In 2010, micro abrasive water jet machining centers became commercially available, because earlier abrasive water jet machining processes were used for meso or macro cutting, not for micro cutting. In around 2013, challenges in feeding fine abrasive particles to cutting heads became feasible. It allowed cutting down to 200 micrometer, and experimentally it became possible to reliably and economically generate cutting jets down to 50 micrometer, because the cutting rate or the material cutting depends upon the cutting jet diameter. Smaller the diameter of the jet, smaller will be the material removal and size of the feature being created. You can see here is the micro abrasive water jet cutting of prototype, flexible patch reinforcement for use following heart surgery. You can see here this fine cut AV and Hanover University was done at Hanover University. You can see here patch reinforcement over here. This kind of the patch can be cut with the help of abrasive water jet, micro abrasive water jet cutting. This is the heart of the human being, as you can see over here, and this kind of the patch, this can be easily cut with the micro abrasive water jet machining process. Now you can see here the photographic view. This is the patch being cut, and this is the jet, abrasive water jet, having the diameter of 300 micrometer diameter. So the feature or the kerf that you are cutting will be slightly more than 300 micrometer size, because overcut is always there in all the processes, and this is a focusing tube. So it is clearly a non-contact machining method. You can clearly see here, this is the abrasive water jet, and there is nothing like a cutting tool that you have in grinding, polishing, or single point turning or milling operations. That's why it is called as non-contact machining method. And abrasive water jet micromachining can be manipulated to produce complex shapes. This is very important requirement, that how to create complex shapes on different types of material. Does not matter electrically conductive or electrically non-conductive, because this is the beauty of this particular process, that it can be applied for all kind of materials. No heat effects or micro cracking on the cut surfaces, and the kerf is burr free, because if burrs are there, they have to be removed before putting a part into the assembly, but this gives you a burr free machined surface. Micro machining and micro milling are the areas for researchers for important contributions in abrasive water jet micro machining processes. Working principle of abrasive water jet machining and abrasive water jet micro machining. This I have shown you in earlier figures also. Here you can see orifice is there, abrasives are coming over here, water jet is coming over here, and this is the mixing tube, and this is the abrasive water jet, and this is the workpiece. So mixing of water jet and stream of abrasive takes place in the mixing tube over here, that you can see, and these are the abrasives. Rapid rise in abrasive velocity occurs in the mixing tube. Once abrasive particles come in contact with the high velocity water jet, then they get the velocity, high velocity, and when impingement of an abrasive on the work material takes place, momentum transfer occurs. When this abrasive particle is impinging on the workpiece surface, momentum transfer takes place. And please note, here the velocity of water may be very, very high. It can be as high as 800 to 900 meter per second. So you can calculate what will be the momentum of the abrasive particles having very low mass, or kinetic energy, which is really responsible in this particular case for the removal of the material from the workpiece. This leads to removal of material by erosion, shear, or brittle fracture. It will depend upon what kind of or what are the properties of workpiece material and where it is cutting. Is it cutting at the top, in the middle, or at the bottom? Pressure is around 400 megapascal. Jet speed maybe as high as 900 meter per second. Cutting in upper part of the curve, that is erosive action takes place. Cutting in lower part of the curve, deformation takes place. And for machining, non-metals, ceramics, composites, rocks, etc., they can be easily cut by this particular process. Metals can also be easily cut by this particular process, like copper, aluminium, tungsten carbide, lead, etc. And operations that you can perform with this particular process include drilling, cutting, deburring, etc. What type of operation is taking place depends upon the relative velocity of the jet and the workpiece surface. Even the turning can be performed. Abrasive water jet turning operation. It can cut any kind of materials, high edge quality, adaptable for remote control. This is very important feature. And recycling of abrasive also takes place, because abrasives are quite expensive and you cannot throw them out after using once. So recycling takes place. Before recycling, they are processed properly. Mechanism of material removal by solid particles, erosion by solid particle impingement in cutting, penetration of cutting edge, plastic deformation to failure. In case of fatigue problem, cyclic failure takes place, brittle fracture takes place on non-cyclic failure, and melting takes place, loss of fluid state. This I have already explained. You can see here, this is the abrasive water jet cutting over here, coming over here, and this is the orifice, and through which the jet will be coming out. Now I have just showed that brittle fracture may take place or plastic deformation may take place. If material is brittle and the abrasive particle is just impacting at 90 degree or just vertical to the workpiece surface, the brittle fracture is going to take place. You can see lateral cracks are there, and once their density increases, these parts will be separated out from the workpiece. In case of plastic deformation, penetration first takes place due to the normal force over here, and there is a shearing force because of which plastic deformation takes place, and you get the chip over here. This chip may be macro chips or micro chips depending upon what normal force is acting and what is the penetration depth in the workpiece. Continuous working principle, mechanism of material removal. Now here you can see whatever I told you in the earlier slide. Different forces are shown over here. This is the force Fy is responsible for penetration. This force is acting in this direction. This is the abrasive particle, here is the workpiece. So this is penetrating over there. And then there is the Fx. This is the Fx force, as you can see here, and it is moving this abrasive particle after penetration in this particular direction, so that it will remove the material in the form of micro or macro chip, responsible for removal of material in the form of chip due to shearing action. Now this is another picture showing the forces, etc. You can see cutting edge and so on. Workpiece is there, water is there, abrasive particles are there, they are moving in this particular direction. Pressure is around 400 megapascal. I have already told you velocity is around 900 meter per second, depending upon what kind of surface you require. It uses kinetic energy of the abrasive particles for removal of the material by fracture or shearing or by deformation, whatever it is. Now, working principle, visualization of abrasive water jet and work interaction. Here you can clearly see this is the entry side. Now this is the jet, and while it is entering into the workpiece, it is exiting from this side itself. So you can see it's not just going straight forward inside the workpiece, it is inclined at an angle theta degree, as you can see here, and h is the depth of penetration. Now you can clearly see here rough surface that you are going to get. That's why I told you reasonably good surface and reasonably good edge quality. because you are not going to get straight or flat surfaces, smooth surfaces in case of abrasive water jet machining as well as abrasive water jet micromachining. Now you can see this is the kind of surface you are getting, and when it reads to the other end, it just exits like this as shown over here. This is the exit cutting stage and this is the entry cutting stage. Now you can see here, this is the surfaces or the edges that you are going to get, and this is the surface at the bottom, and this is the trajectory of the abrasive water jet. This is the another side. So depending upon angle of impingement, erosion, brittle fracture, deformation of work surface takes place. As you can see here, angle of impingement will decide here also whether it is deformation or shearing or brittle fracture. Because in brittle fracture, I told you in the last earlier slide that the abrasive particle has to hit at about 90 degree or vertical to the workpiece surface, and the workpiece material has to be brittle. Machine tools elements, abrasive water jet micromachining and abrasive water jet machining machine tools of a system. You can see here these are the purchased machine tools, commercial machine tools available in the market. You can see here the this is the photographic view in the front side, and this is the detail. You can see abrasive particles is filled in this pot, and this is the nozzle through which abrasive water jet will be coming out, and this is the workpiece which is to be machined. You can see here, not very clear over here, here it is cutting is taking place. This is the another view showing different features of this. Now you can see here cutting has taken place at this particular point. So these are the abrasive etc. different elements of the machine that is shown over here. High pressure water is coming over here. Jewel orifice is there through which the water jet is coming out. Abrasive particles are coming from this particular tube and they are mixing with the water jet over here, and you will get the mixing tube, and this is the focusing tube, and abrasive water jet you are going to get over here. This is quite expensive machine, but it works very well. This is taken from the book chapter of Miller. I had already given you the reference of this. Abrasive water jet CNC cutting machine. Here you feed the program, and then according to the program, the jet or the workpiece or the both will keep moving to create the specified features in the program. So CNC control panel is there, nozzle is there, and other features are. Now this is the abrasive water jet which is cutting over here workpiece surface. Now depending upon the kind of the feature you want and the size of the nozzle, you will get either micro cutting or macro cutting. And this is the cut part of the workpiece, as you can clearly see over here. It is moving in this particular direction. And you can assess not very neat and clean edge over here. Photographic view of abrasive water jet cutting machine. Another machine is there which was available at that point of time at IIT Madras, Chennai. Demineralization plant is here for cleaning the water. High pressure intensifier is there. Then you have the mixing chamber over here in this particular case. And then you have the control panel for controlling different parameters in the while machining. You have the CNC controller. You have the gantry type CNC workpiece, work shell over here. Workpiece is kept over here, where I am showing the secondary nozzle is there. And this machine was purchased by Professor Ramesh Babu of IIT Madras, Chennai under the DST project. This is another machine picture which you can see over here. So what I mean to say here is different manufacturers are providing different kind of the machine, and it cost few crores of rupees in Indian rupees. Same thing is over here. Nozzle is here jet is there, workpiece is there, panel is there. This is a fine cut. You can, this is very important to see over here. This is what I told you, semi scanning electron microscope images from different locations of the cutting front. So you can see here the cut surfaces are not very fine. Its intensity will depend upon what parameters, machining parameters or cutting parameters you are choosing, and what are the properties of the workpiece material. If it is a composite, definitely you are going to get the rough surfaces, more rough surfaces. Now you can see here separation cut. So this is the surface over here, rough cut, clean cut, fine cut and extra fine cut. So what I mean to say here is, depending upon your requirement, you can have different categories of the machined surfaces. Elements of abrasive water jet system, machining system, pumping system is there, abrasive feed system is there, water jet system is there, nozzle and catcher is there. Catcher plays very important role. I will show you. Pumping system, you have the intensifier which can give you as high as 415 megapascal. You have 75 HP motor over there, but it depends upon the capacity of the motor. It can be 75, it can be 70 or 65. You have the high velocity jet. Then you have the abrasive feed system. I have shown you in the pictures already. It delivers dry abrasive. This is very important. Abrasive should be dry. To control flow rate, control orifice diameter and suction in mixing tube. It cannot supply abrasives over long distances, because this abrasive feed system normally is not capable to supply abrasive particles for long distances. So what they do, they use directly slurry. Slurry is the one, as I mentioned you earlier, where medium is there, liquid medium is there, it is having the abrasive particles mixed with it, that is known as slurry. To feed over a long distance and more power is required in that particular case. Water jet nozzle diameter is around 75 to 635 micrometer depending upon your requirement, sets the limit for cut dimensions also. And for high life of nozzle, sapphire material for making the nozzle is used, because it is very hard and its wear rate is much smaller than other types of the nozzles. Abrasive jet nozzles, it functions of a nozzle in abrasive water jet machining is mixing of abrasives and water, forming high velocity jet, and this high velocity jet having high kinetic energy is going to hit the workpiece surface to remove the material. And materials of a nozzle normally used are tungsten carbide, boron carbide, sapphire, etc. There are two basic methods of generating abrasive water jet. Abrasive particles can be suspended in pressurized water to form slurry, and the slurry passed through a cutting nozzle. Second one is, pressurized water can be passed through an orifice or nozzle to generate a high speed water jet, and abrasive particles entrained into the jet. It is more clear from this. Here you can see here, this is a high pressure pump, suspension, then abrasive particles, abrasive mixture vessel, both are getting mixed up, water jet as well as abrasive particles, and you have the cutting head is there and abrasive water jet is coming over here. But in this particular case, you have the abrasive hooper. This is coming, abrasive on off is coming over here, and ultra high pressure pump is there. So water jet is coming from here, and both of them are mixing in the mixing tube, and then you have the abrasive water jet over here. So you can see here are the different shapes and sizes of the abrasive particles. They are, all of them are micron dimensions or nano dimensions in certain cases. SEM micrographs of abrasive particles. Now these are the different shapes that you can have of abrasive particles. Typical shapes of garnet abrasives used for abrasive water jet machining. Types of abrasive jet nozzles. You can have single jet side feed nozzle. I will show you the picture. You can see here, this is the single jet coming over here, and from side you are feeding the abrasive particles, and you have the abrasive water jet nozzle over here, and this is the workpiece, and the distance from the surface being cut and the bottom of the nozzle is known as nozzle tip distance. This is the target, that is the workpiece, nozzle, and this is the mixing over there. It is simple to make, but rapid wear of exit part of nozzle. Here, because here abrasive particles are hitting the nozzle, so the wear of the nozzle takes place faster. Non-optimal efficiency of mixing of water and abrasive. Mixing is non-optimal in this particular case. You have annular jet central feed nozzle. This is another type of the nozzle. You can see here annular jet is coming, water is coming from the side, this one, and here is the abrasive particles, and both of them are mixing here outside the nozzle over here. They are mixing over here, which is little bit outside the nozzle. So you can see here better mixing of water and abrasive particles. Mixing is outside the nozzle, less accurate machining compared to other type of the nozzles. Cuts are wider. As you can see, it is widening as it is separating out from this nozzle, and so definitely the cut size will be wider. But if you see here, it is concentrated in this particular case. So the cut size is smaller in this case compared to this particular case. Then you have the multiple jet central feed nozzle. As you can see over here, this is the water jet, this is the water jet. You can have more than two types of water jet, two numbers in water jet, and this is the abrasive particles. Both of them are getting mixed up in here in the tube itself, and you have the target nozzle tip distance is there, and centrally located abrasive feed system, that is the centrally located abrasive feed system here, and then you have the surrounded by multiple water jets in a converging annulus. These are the multiple water jets, and they are converging over here where they are mixing to the abrasive particles. Higher nozzle life and better mixing. Difficult and costly to fabricate. Here nozzle life is higher because they are mixing over here where you have enough space over there. Maybe other types also. These are the three types I have shown, but nozzles may be other types also. Types of catchers. There are two types of catchers commonly used in these machine tools: stationary nozzle and moving workpiece. Now you can see here, this nozzle is stationary, but workpiece is moving as shown over here, either in the left side or the right side, depending upon the required feature. And you can see here a long narrow tube placed under the point of cut. This is the point of cut, and just below this you have the long narrow tube over here, and these are the obstructions to reduce the jet velocity, because I mentioned to you that jet velocity may be as high as 800-900 meter per second. So it should be reduced before the water enters into the tank, otherwise it will cut the tank itself. So it is reduced with the help of these obstructions over there and before it exits. Another one is moving nozzle and stationary workpiece. Here workpiece is stationary but nozzle is moving. This is the nozzle which is moving on the left side or right side depending upon the shape of the feature to be created, and here is the workpiece. This is the workpiece, and this is the water tank where this abrasive water jet will get filled up. Now this is the set known as settling tank. and the high velocity jet hitting the settling tank water. This is the water. Now here one has to be careful, either height should be quite high or the jet velocity should be comparatively lower so that it does not damage the tank itself. A water filled settling tank underneath the workpiece, workpiece is here. Transfer of high pressure to water filled in the tank takes place. To collect the remains of abrasive water jet, there is a flexible hose. Pressure is less than 24 megapascal, not shown over here. That hose is not shown over here. And there is a rigid tubing through which you remove these remains from the tank. Now this is the simple schematic view. This is the nozzle, this is the workpiece, and this is the obstruction to reduce the energy, and this is the exit over here from here. And this is the second type, this type where water jet, abrasive water jet is here, workpiece is here, water tank is over here. Parametric analysis of abrasive water jet machining and abrasive water jet micromachining. Fishbone diagram for abrasive water jet machining. Now this is the fishbone diagram where main parameters are like water, water nozzle, workpiece, abrasive feed nozzle, cutting parameter, mixing tube. And here are the responses which you are normally going to measure, that is the machining rate or material removal rate, quality of the cut, kerf quality, depth of cut. In quality of the cut you can have the dimensions also so that you can get the tolerances or the dimensional accuracy. Now process parameters as shown over there, responses are there. Water, you have flow rate and pressure, that is you can see here, pressure is there, flow rate is there. Abrasives type, size and flow rate are there. Then you have water and abrasive jet nozzle, what is the material of the nozzle and what is the design of the nozzle, that makes a difference. Cutting parameters are feed rate, stand off distance, and workpiece material is another one. Now then you have the mixing tube. Now in the workpiece material you can see the hardness is important, whether it is brittle or ductile, that is also important, and what are the material mechanical properties and other properties. Then you have the mixing tube, diameter and length, this is another parameter. Then you have the angle of cutting, that makes a difference, as I have shown to you earlier also while dealing with the surface being produced. Traverse speed is another parameter, and number of passes, how many passes you are having. When we say abrasive feed nozzle, material and cross section are important. Cutting parameters I have already told you, stand off distance or nozzle tip distance, angle of cutting, and mixing tube length and number of passage. Effect of abrasive water jet pressure. You can see here, this is the pressure over here, and this is the depth of cut, and this is the abrasive flow rate. As abrasive flow rate is increasing, depth of cut is also increasing. And this is important to note here, critical pressure. Before critical pressure is reached, there is no cutting, because each material has its own properties, that is strength, hardness. Now unless these abrasive particles have enough kinetic energy to cut that particular material, you cannot have any depth of cut. That's why this is the critical pressure for this particular combination of parameters, machining parameters and workpiece material. Critical pressure, below this pressure no cutting takes place, that I have already told you, because low kinetic energy, different for different workpiece material. This critical pressure will depend upon the properties of the workpiece material. It depends on the workpiece properties, hardness, ductility, etc. Above a definite jet pressure, machine depth tends to stabilize. As you can see here, after a certain pressure, it will more or less stabilize over there. Relationship with machine depth is steeper with higher abrasive flow rate, as I have shown to you, that is shown over here with the arrow. Higher the flow rate, steeper or higher the depth of the cut. Increased pressure will lead to higher cost of, this is very important to note, you cannot keep on increasing the pressure of the water jet because higher cost of pump maintenance, low efficiency at very high pressure, and higher nozzle wear rate. So that means cost of cutting will increase finally. This is another important chart. As pressure is increasing, these are the experimental points. As you can see here, depth of cut is also increasing. And you can see here, this is depth of cut, again water jet pressure separately, this is abrasive water jet pressure, and here you can see this is the critical pressure and this is another critical pressure where this is different for different nozzles, right? Because area on which cutting is taking place is varying. So definitely water jet pressure has to be different. These are the again experimental results, pressure in megapascal, and this is the depth of cut for another material in large view over there, and these are the different conditions, flow rate are there, so many kg per minute. So as this is increasing, this is sixth one, 0.106 kg per minute, this is giving the highest depth of cut, and 0.032 kg per minute, it is giving the lowest one. Again here you can note the critical pressure is there. Below this, no cutting is taking place. Abrasive flow rate, water flow rate, water propelling fluid enables high abrasive flow rate up to 5 kg per minute. Abrasive velocity, it can be normally 300 meters per second. Please note, this is the abrasive velocity, not water jet velocity. Abrasive water jets are coherent, hence more suitable for cutting. Q dot is proportional to under root pressure. Q dot is also directly proportional to diameter of the nozzle. Abrasive flow rate, m dot c, is proportional to Vp square m dot. Now you can see here, this is abrasive flow rate, this is depth of cut, this is for glass bead, this is silica sand, this is granite sand, and this is for alumina. So you can see over here, abrasive flow rate, machine depth. Now Vp is the particle velocity, and this you can see over here, this is mixed up. So this m dot c is directly proportional to Vp square m dot, where increase in abrasive flow rate beyond the critical value would reduce machine depth. So you cannot keep on increasing the abrasive flow rate, otherwise beyond a certain point it will start reducing the machine depth. Increase in abrasive flow rate, there will be higher increased wear of the mixing nozzle and reduced mixing efficiency will be obtained. Criteria for selection of the type of the abrasive, because as I mentioned earlier also, there are different types of the abrasives available in the market. So what are the criteria for selecting a particular type of the abrasive particles? You must look into the cost of the abrasive particles, nozzle wear rate of the due to the abrasive particles, environment considerations, because when we say nozzle wear rate, you have to consider the material of the nozzle as well as material of the abrasive, which will decide which is going to be economic. Then you have the machining rate and particle strength, that is abrasive particle strength. So all these things have to be considered while selecting a type of abrasive particle. So you can see here, what I have mentioned over here is that these are the different types of the abrasive particles. Pressure is the same, but depth of cut is different. Glass beads minimum depth of cut, then silica particles, steel particles, granite particles, and these are the alumina particles. So depending upon the hardness of the abrasive particles, you are going to get different depth of machining. Abrasive particle size, optimum particle size should be selected to get a good dimensional accuracy, because dimensional accuracy will be decided by the abrasive particle size also. Finer particles are used for shallow depth of cut, while coarse particles are used for high depth of cut. Different abrasive sizes for different depth of cut. Abrasive materials, machine depth is a function of the type of abrasive particle. Effect of traverse speed, as you can see here, traverse speed is increasing, depth of cut is decreasing in this particular case. And here you can see there is the area generation rate. As traverse speed is increasing, there is the optimum obtained over there, and then this is decreasing. Let us understand this. As traverse speed is increasing, depth of cut is decreasing, because the time required to cut the material is decreasing. That's why depth of cut is also decreasing. Here traverse speed is increasing up to certain point, area generation is increasing, because area gets increased as the traverse speed is increasing, area being machined gets increased. But beyond a certain traverse speed, as earlier mentioned, also the area gets reduced, because it does not get sufficient time to remove the material from the larger area, much larger area. So depth of cut decreases with an increase in traverse rate, which may be within 10 mm per second, as shown over here. Overcut decreases with an increase in traverse speed. Traverse speed versus area generation rate has an optimum, as shown over here. Area generation rate may be as good as 2000 millimeter square per second. Number of passes, you can have multiple passes, because if depth of cut is small and you want to cut it for a larger depth, mostly you have to have the multiple passes, because single pass normally in micromachining, yes, it is fine for single pass. If it is macro machining, you will have to have many passes rather than only one pass. Multiple passes, single water jet with multiple passes is there, multiple tandem jets with single pass, I will show you. Each jet makes an additional depth of penetration. Jet 1 gives H1 millimeter, as you can see over here, this is the jet 1, it is giving H1, jet 2 giving H2, jet 3 gives H3, means total H3, this is not H2, H2 minus H1, H3 minus H2, that are the cut made by this, and all the three are cutting simultaneously. Increase in number of passes, kerf acts as a local mixing chamber. Now multiple tandem jets, this is for multiple tandem jets with single pass. In single pass, as I mentioned just few minutes back, this will cut H1, this will cut H2 minus H1, and so on. You can see over here cumulative depth of cut over here, and number of passes is here. As number of passes is increasing, cumulative depth of cut is increasing. Now this is TR1, traverse speed during passes. So as traverse speed is decreasing, cumulative depth of cut is decreasing. As traverse speed is increasing, cumulative depth of cut is larger. But again, there are the limits, as we have seen in the earlier slide. So cumulative depth of cut, number of passes is increasing, cumulative depth of cut is increasing, as you can see here. Extent of distance, this is very important parameter in case of abrasive butter jet cutting. Distance between nozzle tip and workpiece surface being hit by abrasive butter jet. As extent of distance increases, machine depth decreases. What happens as extent of distance is increasing, machine depth is decreasing, rebound of particles and loss of energy gives shallower depth of cut. Beyond upper value of extent of distance, no cutting will take place. As you can see here, as the extent of distance is increasing, depth of cut is continuously decreasing, and beyond a certain value of extent of distance, no cutting will take place, because once extent of distance increases, kinetic energy of the abrasive particle is not sufficient to remove the material from the workpiece. A smaller extent of distance gives deeper cut, as you can see over here. Extent of distance normally varies around tenths of millimeters. So you can see here depth of cut, as extent of distance is increasing, depth of cut is continuously decreasing. So effect of extent of distance on depth of cut, and you can see here other details are given over here. Visualization and applications, quickly I will show you. Visualization of abrasive water jet cutting process. As you can see here, this is taken from Ashish paper. Abrasive water jet kerf, this is known as kerf. The distance between two sides of this cut is known as kerf. Nozzle perspex is there. Here intermixing is taking place, clamp is there, and this is moving table. So jet is stationary, table is moving. By tilting the workpiece or the nozzle, cutting would take place at different angles of impact, and impact angle is very important. As I have already mentioned, there are two modes of material removal take place. Cutting mode in case of shallow angle of impact, and deformation mode takes place at larger angle of impact. Now penetration rate and depth of cut, they are the function of time, keeping other parameters as constant. This is penetration depth, penetration rate and depth of cut is function of time, provided you keep all other parameters constant. Process performance, it can cut thick materials as thick as 2200 millimeters. Kerf width decreases as workpiece hardness increases. This is another important parameter. Machined surfaces, there is no thermal damage, no thermal or mechanical damage. Machining of glass, stray cutting leads to frosting of the surfaces, and this process can be used for frosting of glasses at many places. Applications, materials, industries and operations. It can be used for metals as well as non-metals. Also, it can non-metals like ceramics, composites, rocks, etc. can be cut. In metals, copper, aluminum, tungsten carbide, lead, etc. can be cut. Omnidirectional cutting with no worth. No worth is very important. Industries where it is used and it can be used are aerospace, nuclear, foundries, construction, etc. And steel components cut plates, tubes, corrugated structure, etc. because in many cases cutting of large plates or tubes or corrugated structure is a problem. So this process can be used. Operations that can be performed are drilling, cutting, deburring, etc. It can cut any kind of material with reasonably good edge quality. I don't say high good edge quality, but reasonably good edge quality. It is adaptable for remote control, recycling of abrasives. I have already mentioned recycling of abrasive particles is always done because abrasives are very expensive. You cannot afford to throw it out after using it once. Applications. Now you can see here cutting of 4i laboratory and SMD09 words on aluminum sheets. This is the one, this is the actual taken out, and this was done at IIT Kanpur. And you can see here separated out male and female parts, 4i lab and words cut from aluminum sheets. You can see here, this is the female and this is the male part. These are the quality of honeycomb structure cut by an abrasive water jet, and these are the material removal characteristics in a fiber reinforced epoxy. I told you earlier that whenever you have the composite material, you cannot get very good surface finish. So you can see here, these are the fiber particles protruding outside the bonding material over here, fibers are here. So surface roughness is going to be very poor depending upon the difference in the properties of the material that are being forming the composite material. Now you can see the poor pocket formation in soft concrete, so you cannot find very good edge quality and very good dimensional accuracy, but it can be controlled and you can get good edge quality under certain conditions. You have to optimize the parameters for different kind of materials. These are the different structures that were cut by Miller. Profile in 50 micrometer thick stainless steel cut with 300 nanometer aluminum oxide particles in a 40 micrometer. Noted, nanometer particles are used for cutting such kind of 50 micrometer thick stainless sheet. Here you can see profiles cut with a 50 micrometer diameter ASJ in metals, glass, plastic, etc. And these are the features that have been cut on different sheets over here. These are the different features that have been removed from here. You can see here ceramic structure with voids. Test parts with 80 micrometer and 125 micrometer diameter abrasive butter jet generated by entraining abrasive slurry. This is again from Miller company. You can see the size of the components or the element that have been fabricated, and this is the one setup we have already seen, and this is used for abrasive water jet turning operation. Here workpiece is rotating, abrasive water jet is here, which is removing the material from the workpiece, and you can see the side view, and this is the abrasive water jet and this is the workpiece surface, circular surface from which material is being removed. So principle and geometry of abrasive water jet turning operation. Now these are the other examples which you can see here. Cutting applications with high pressure water jets, plastics, plain water jet, and marble abrasive water jet. This is the marble, this is the plastic being cut, and this is the abrasive water jet turning, which I have already shown you in the earlier slide. This is rotating workpiece, threads are being cut. This is the abrasive water jet, this is the side view. Now these are the kind of the features created or cavity formed over here. These are the threads profile machined by abrasive water jet. Here are the threads that are, so this is a enlarged view of these thread profile being cut over there. Now these are the again different types of the features that have been machined at IIT Madras, Chennai on the granite cutting. So very nice feature that have been done. It was obtained from the lecture of Professor Ramesh Babu of IIT Madras. Conclusions. It is concluded that abrasive water jet cutting process is useful for machining metallic as well as non-metallic materials. Parts with reasonably good accuracy can be machined. Abrasive water jet cutting has applications in different kinds of industries. The process has applications in macro cutting as well as micro cutting with appropriate selection of input parameters and device including nozzle, etc. Thank you very much.